Okay, so let's continue. So we are discussing the de-Rham theory. So if you start with a manifold M, the space of its symmetry is called the group of diffeomorphism. So it acts on M. Okay, so because it moves, so by definition, this is the space of all symmetries, so it acts on M. So therefore, in particular, it acts on its smooth functions by composing the functions with a diffeomorphism. Okay, so that's a actions. Okay, and sometimes you also write this as the sections of the trivial bundle. So this is just M cross R trivial as a trivial vector bundle over M. Now you get an action of the group, and so you can look at its Lie algebra actions. So this is the infinitesimal actions. So because if you move the diffeomorphism, move a little bit, that is a direction of the moving, which is a vector field. Okay, so therefore this one will act on the space of all functions. Okay. So sometimes you can write this in the following way: that if V is a vector field, and you can usually look at this with a family. This will be a group of diffeomorphism for a T in real number. Okay. So this one add on the functions, and then ddt t equal to 0. Okay. And that is the vector field acting on the function. It's just a usual differentiation of a function along a directions. And so these actions, V acting on F, has the following property that it only differentiates F. It does not differentiate V. I mean, it's linear in V. Okay. So this is linear in V. Okay. So you can write it as a something on V. Okay. So now this is this thing acting on V never differentiate V. Okay. This one differentiate F, but if you write it this way, fix the F, then this one does not depend. Is a tensor in V, and let's just call that dF. So at the moment, this is a notation. Then you start from F, you get something which is acting linear on V. So it means that you can start with a F. Okay, so this is F here. You get something which acts linear on V. So this is a sections of the cotangent bundle called dF. Okay, so that is so it's a dual perspective, and call this operation D. Okay, so it's the same information. One is the V acting on F, and then we dually is sending F to this operation on linear thing, linearly on V. Okay. Now, you have to use the following property that this is a group, Lie group, and this is a Lie algebra. So that group structure is telling you that there is a Lie bracket here satisfy the following two properties. So this, and then the Jacobi identity, U, V, W. So U, V, W, V, W, U, W, U, V equal to 0. Okay. So these two property is in general, if you're a group, then the Lie algebra, the group structure, if you look at the Taylor expansion, then the first two information about group structure is these two data. And if you from the perspective of the manifold, this information, the reason that this is true is because so this is because if you take any functions, if you differentiate twice in the first coordinate, second coordinate, or the second coordinate, the first coordinate, are the same. This is the Fubini field. Okay, so this is really the reason that if you check directly, that this is true. Okay, it's the same as this property. Now, how about this information on this side? Okay, so now we're going to say that this information is allow you to continue to look at this differentiation. Now we're going to write this at omega 1m, just for simplicity. So if you look at wedge 2 is related to this side is skew symmetric on that side. Okay, so that will be skew symmetric here. And this is called omega 2. Okay, those two information is telling you that you can continue to define this D and satisfy the following property, D squared equal to 0. Okay, so both of these is also the same reason as this, which is also the same reason as this is in the algebra data. Okay, so this is just equivalent information that the manifold act on by the diffeomorphism group and act on function, and that group action data become, on the dual perspective, become a differential. This is called the DeRham complex. Okay. So D squared equals 0 tells us that, so this statement is the same that the image of D, if you do it twice, is inside kernel of D. Okay, and so you can look at the differences, and which is what we call the DeRham cohomology. Okay, sometimes to distinguish, let's say DeRham here, is just to measure when this is how far this is far away from being equal, meaning that how far it is away from being exact sequence. Okay. These are definitions. This is kernel of D, divide the image of D. When we are all looking at things on the omega k level. Okay. And so if you just look at this, how can we compute anything like how to compute this? Okay, this turned out to be very easy to compute. Okay, and of course not from definition. There's no way that you can write down all this form and then write down differential and check that. It's not possible. Okay, and there are a couple important tricks. Okay, to compute this. As I mentioned, again, this turned out to be very easy to compute. The first property is this is defined by differentiations, and for the fundamental theorem of calculus, that there's an inverse. It's called integration. So in some sense, that this is kind of locally, it looks like exact, because locally, integration and differentiation are inverse to each other. So roughly speaking, this is exact. So this is supposed to be very small. The difference is very small. Okay? They found a dimensional. Okay? So the first statement, sometimes we call it the Poincare lemma, which is just the fundamental theorem of calculus. It's just meaning differentiation and integration are inverse to each other. So we rewrite in the manifold language, then it's called Poincare lemma. It says the following. It just integrate on R, okay? It says that if you look at M cross R, you can project to M by pi, and then you can look at include this to the 0 here, and that's called S. Okay, and so this one will give you a differential form. And this one, differential form, just like functions. Okay, you can compose the map. Okay, so it's a pullback differential form, just like pullback functions. So the pi to here, you pull back form here. This is called pi star. You pull back that, it's called S star. Okay. and they are inverse to each other up to something that you want to quotient away. Okay? Because the thing is defined as a quotient. Okay? So this one satisfies that 1 minus S star compose pi star. This one is exactly 0, but the other one is up to a side, it doesn't really matter, up to this. Okay? So that, if this is the case here, on the cohomology level, they are the same. Because if you're in the kernel, so this is 0. And then the difference is d of something. Well, this is in a quotient. So therefore, anything, this is called homotopy operator. That means that on the cohomology, this effect is like 0. Okay? So that tells us that cohomology of M cross R under these two maps are inverse to each other. So either pi star or S star is isomorphic. In each degree, I mean, for each k, this is true. Okay? And the homotopy operator is integrations. Okay? So it's the same as integration and differentiation statement. And why it says a two-term here? Because if you first differentiate and then integrate, then you get the boundary value of 0 and 1. Okay, so that's why this is two terms. 0 is because S is 0. Okay, so that's two terms. Okay. So D is the integration. It's no surprise. So differentiation, integration are cap inverse up to boundary value. Okay, there's a variation here. Okay, first of all, this immediately tells you how to compute it for Rn. Because for R0, which is just 1 point, of course you know all the differential form. There's no differential form, there's only constant function, nothing else. So this is just the whole cohomology is just R. And this is inductively telling you that the same is true for all Rn. Okay. Okay, there's a variation. Is you can do exactly this differential form. Thing. If you only look at those forms with compact support. So just like functions, where non-zero place is a compact set. Of course, this only different if M is non-compact. Of course, if M is compact, everything has compact support. Okay, so and the reason is if it has compact support, the differentiation has compact support. Okay, so you can do exactly the same thing and define you the cohomology with compact support. Okay, same because d squared is 0 and so on. Okay, so this is compact support cohomology. These are comparative support form, comparative support, or whatever, cohomology, let's say. And you can also do this argument here, except that this one here, except now differential integration has a trouble. When you differentiate comparative support, it's still comparative support, of course, but integration is not. Okay, integration is just become non-compact support. So you have to subtract the whole thing back, and that was what I explained last time, that in this case, you get the following. Then you get omega 0 M cross R, omega 0 M. Okay. So in this case, what we do is this one is a pi star. It's an integration. Previously, this is just pullback, inclusion, and so on. Okay. So that is the same K form become K form and so on. But now this is integrate, when the lower star is the integration along the R direction. Okay? Whatever here, R. So you have to, once you integrate, you take away the dt direction. So this is T variable, let's say. So that will go from a form of degree K to a form of degree K minus 1. Okay? The reason is if you try to do the pullback, well, if this one is compacted support, pullback is not because R is not compact. Okay? So pullback is not because of compacted support. Integration is. So the direction is reversed. Okay? Here, there's a map. Okay? You get a form of degree K minus 1 to a form of degree K plus K here. And the E star is whatever form you have, you wedge with on this particular form. You take any form of this type. So it's a bound function, and this bound function, called this eta, T, has compact support, and then the total integral is 1. Okay, so you just send whatever here, and then you make the form here to be compacted support. Yeah, so that's why you have to multiply by some one form, which itself is compacted support in all directions. Okay. Now, because this integral is exactly 1, so therefore, if you push it and integrate back, you get back the original 1. Okay. So now this is the other way around. So this satisfies pi star compose E star equal to 0 as before. And the derivative reverse is plus minus dk plus minus kd. Okay? And k is the one that it's also a suitable integration, but you have to use this to help to make sure that it's compacted support. Okay? So we'll write that last time. And again, you get the same thing here, except the difference is the isomorphism is shifted degree by 1. Okay? So you get cohomology. Sorry. Here. These are compacted support form. Okay. So you get cohomology of M cross R isomorphic. So either pi star or reverse is D star to cohomology of K of M. If you're looking at a compacted support form, the degree has to be shifted by 1. Okay? So therefore, if you look at cohomology, so of course cohomology of R's of 1 point, the real vector space of dimension 0 is just 1 point. Okay? Of course, this one, that's 1 point, so it is R when the degree is 0, and otherwise it's nothing, right? Because it's only constant function. Oh, it's just 1 point, and it's just R. There's nothing else. Okay, so you can either run. So in this case, whether compactly support one or non-compactly support one, there's no difference because 1 point is compact. Right? So you can compare. So, but now if you want to use this to look at R2, R3, R4, okay, then if you not compactly support, the same is true for Rn. You only concentrating on degree 0 because this isomorphism does not shift degree. So it's 0, it's R, and then all the rest is 0. Okay? But if you are doing this, each time you go up dimension, it shifts the degree by 1 upper. Okay? So therefore, if you look at compactly support cohomology of Rn, then you only have R at the top degree, and otherwise always 0. Okay? In fact, there's a relation between these two that we involved n here. The point is, so you see that if you look at hk of Rn, and if you look at hn minus k of Rn with compactly support, then these two are either the same, they're always minus k. These are always the same, okay? Because this is shift by n, okay? In fact, they're naturally due to each other. So that is a map reducing the duality. This is just integrations. If you look at the wedge product of that, so this one follow from, this is right here. That if you look at just on the level of differential form, so you look at k form and n minus k form, and then you wedge together, it becomes a top degree form, and then you can integrate to get R. Well, except that when you integrate, you better make sure that it's finite. So therefore, you need some decay property of the product. The product function has to be finite. And the way that we're doing here, there are various ways, but the way we're doing it, if the product, if this one is compactly support, that would be good. Okay? So you only need one of them to be compactly support, because if one form is compactly support, the other one is not, the support is in the smaller one. Okay? So you can, so once you require one of them is compactly support, this one is well defined. Okay? And compatible with D and so on, compatible with all the operations, and that gives you this map. So this is just a product and an integrate. Okay. And the fact and then that shows us that that is the map. That is a perfect pairing. Meaning that these two vector spaces are due to each other induced by this bilinear map. Okay? This is naturally due by this pairing. Defined by that. Okay. So we compute something. So first of all, you see that why this cohomology seems the definition is complicated, but should be finite dimension. But because first of all, if you have only Rn, then it is pretty just one dimension. Okay, and any manifold is pieced together by things like that, by finite step basically. So therefore, for any manifold, even though you do not know how to compute it at the moment, you can see that it's finite dimension. Okay? And because of the Grewing argument. But before we talk about the Grewing statement, let me also mention that this property that I just erased, this Poincare lemma argument that I also mentioned last time, imply that this is the homotopy information that imply the following. Remark. This is also from last time, in fact, that if M1 and M2 are homotopy equivalent to each other, then all the cohomology are isomorphic from the cohomology. And this follow, this is also using this Poincare-Lemma argument, as I mentioned last time. Okay. So therefore, in particular, you look at Rn or small open set in Rn, the cohomology are the same. Okay, so that's why I can piece them together. So the piecing together argument is the following. So that will be very powerful. Now, locally we know, and then you can put things together. Okay. And so the second argument is a Green argument, which are called the Mayer-Rhetoric argument. Mayer-Rhetoric. And the point is if you start with any manifold, okay, you can always write the manifold as a union of Ui. So this is a union of Ui. Let's say the manifold either is compact or finite topology, meaning that it can be constructed a finite number of such steps. Okay? It may be non-compact, but at least you don't have to be finite, but it could be the topology, meaning that, for example, you cannot have things which take away infinite number of points which are closer and closer to the points. Okay. You could be a Riemann surface of infinite genus. You just don't want the genus to be getting concentrated to a point. Okay, so if you go further away, things are far apart, this type of thing. Okay, so this type of locally finite topological type. So pretty much everything we will think about is like that. Okay, so any reasonable manifold will have a property that is an index set. So as I said, may not even need to be finite. Okay, but for many cases we usually think of finite anyway. So let's pretend it's finite. Okay. It's not an important assumption. So we can, the point is each of that is a, you can think about it as a open domain or a ball, or up to scaling is like Rn, up to homomorphism, it's not important. So let's say, this spun is like a ball, let's say, okay, or Rn. And put them together, let's say ball, okay. And the homotopy equivalent anyway. Now, the point is that we need all the intersections are always of this type. Okay? More than this, it's like this one. The intersection of two of them is also like a ball. The intersection of three of them is also like a ball. Okay? So therefore, if you look at any I1 intersect I2, any finite number of such intersections is also diffeomorphic to a ball. Okay. So if you have such a thing, it's always true for any Riemannian manifold. If you have such a thing, then basically all the gluing arguments tell you if you know how to do it for one ball and then two balls together, and then you can keep on gluing it. Okay. And that was the Mayer-Rhetoric argument to go from finite for standard piece to glue them. And the existence of this is recent. If you choose a Riemannian metric, so manifold is a second countable and all this, so that argument you can use partition unity to choose a metric, Riemannian metric. Okay, and then you have to assume that the metric has lower bound in finite part. You have a lower bound in the injectivity radius. So you do not want just like that. You do not want those small loops to be concentrated very tiny to zero size. Okay, so make sure that at every point you can write a geodesic ball. Okay, and then so you can choose UI to be really, with respect to Riemannian metric, to be sum of the points Pi and then look at some geodesic ball of radius epsilon. If you choose epsilon small enough, then they will have this property. And because of geodesic convexity property of that. So not just the ball itself, the intersection will all have this property. Okay? So this is some geodesic positivity, geodesic convexity. Geodesic ball has some convexity. The reason is basically that a fundamental theorem of Riemannian geometry says that given any Riemannian metric, it looks like the standard metric on Rn up to second order. If you are on Rn, of course you can do that. Okay? And up to second order, that is true, and then you can do that for any manifold. Okay, so that was the reason. Okay, so once of this, then they reduce to, if you have two, so you can just inductively group more and more balls together. So reduce to extent, and then to this two. So let's say only have two of them. So U, V, and this is U intercept V. Okay. So the manifold is just a U union V. Okay. So you can start with two, and then you get more later. Okay. For this argument, at the moment, you do not need U and V to be ball. Okay. You just say that whatever you know about U and V, then you can keep on making bigger. Okay. And so you get U destroy union V as a map to here, because U map to V, U map to M, V map to M. Okay. And then the intersections we have two map. So the intersection is inside U, the intersection is also inside V. So this has two map. Okay. So got this 0, 1. Okay. If you have a free term, then if you have a free ball UVW, then you also have U intercept V, U intercept W, and then you have free map and so on. Okay, it's just it's the same argument. Okay, so this is this is the essence of the argument here. Then you get a differential form on M. You pull it back to differential form on the destroy union, which is this differential form on this. And then you pull it back. But now you have two maps. So you use both of them to pull back. Okay, because this is a linear space, you can subtract them. And the statement is the clear point is this one is surjective. And that the argument, as I mentioned, that uses partition of unity. Partition of unity. Okay, the reason is that if you have a U here, and then V here, so this is U, this is V. So this one is the U intercept V. And then you have a form here. Okay, it's only defined here. But then this form may not descend upstairs. Okay? But if you look at this one, it descends upstairs here. Look at that one, descend upstairs, descend the other one. So you can do a partition of unity, cut it, and then each one descend to one side of that. Okay, so that was the argument. So what I mentioned last time. So you get a short excess sequence of complexes. So all of these come with the D here, and D here, and they're compatible with that. So this is not just a vector space excess sequence, this is the excess sequence for the complexes, and that induces you a long excess sequence in cohomology. So you get long excess sequence. in cohomology. So for example, if you know U and V, and then the information or how they're related, then you can know the information of M. So that's how you put it together. So what are the examples of this type of argument? So you can do it two, and then you can do it all of them, many of them. So application is the Thom isomorphism. So what's a Thom isomorphism? Well, we know that if you look at our K, our N, I use, okay, our N, okay. Good point. And we know that the compactly support cohomology is K, okay, and is isomorphic to N plus K is isomorphic to K. Right? Because this is when you're shifting by R, then each compactly support cohomology, you shift the degree by 1. Okay, so you can only get Rn, the n fund, and then you don't get anything. Okay. And therefore, it's the same if you multiply this by a ball. So let's say U is like a ball. Okay. Well, except that we are only doing this integration on the fiber directions. Okay. There's only compactly support in the fiber direction. You don't do anything on the horizontal direction. Everything is fiber-wise directions. So these are vertically compact. Okay? So this is only compact in the Rn directions. Nothing about the U direction. U direction you don't care. Okay? Just all the fiber direction is compactly support. So these are vertically compact support. Vertically compactly support. That means all the Rn directions is compactly support. Okay, so this is the argument using this Poincare lemma, right? This integration by part type argument for the compactly support set. So it's true for U, and it's true for V, it's true for U intercept V. And it's true for U unit V. And then you can keep on 2, 3, 4, any ball. Okay? So then the Maria-Torres argument. If you want to see more the detail, you can, for example, look at this famous book by Borgen 2, Differential Form in Algebraic Topology. We'll give you the more detailed explanation, but there was a point that you know this is true on a, so you take any manifold M, take any vector bundle, this one, okay, and then you write the M as a union of all this UI, and then you start to prove the thing, you try to prove the thing on here, meaning that if you look at the N is this diagram, plus K cohomology of the total space of this bundle, but vertically compact support form, and then the integration here to the K form on the base. This is isomorphism. Okay, that's called the Thom isomorphism. Okay. And the proof is what I said. So you first argue that this is true when M, when you choose M to be a very small ball, then the bundle is trivial, so they look like this. Okay, and then you choose for one ball, U and V, and intersection, you get 2, and then 3 and 4, and so on. Okay, so my rhetoric argument proves this tau isomorphism. So in particular, you see that you have an element 1 here, which is in H0 of M, constant function 1, right? 1. So it's a closed form, right? Function 1 constant. And so that should correspond to an element here, right? So because this is isomorphism, and that should correspond to some element here. Did I call it phi? I don't know. Tom class T. I don't know, phi? Okay. So that should correspond to an element here under this isomorphism. So that should be some element here. Okay. And if you think about what is this element that I told you earlier, well, just you need to argue it for on a small ball. Well, this element is the following. Let's say M is a point, and this one is just Rn. So this is Rn here, this is a 0. R1, I'm drawing R1 here. Okay. And now you want a one form, right? This one is in H0, so this one is in Hn vertically convex support. Now in our case, E is just Rn. And so this is going to be n is 1, there's just one form, and the one form is this one, exactly this one. It's this eta t dt, such that integrate on R eta tt is 1. It's this bound function that we choose, okay? And so this is that one, okay? And if you have a U here, if this is the Rn, you just bump on our Rn, dt1, dt2, it's just product of such, basically, if you like. Okay, this is Rn you look at. If you look at R2, you look like this. R2, you look at the product of these two, so it look like that function. Okay, this function times dt1, dt2. Okay, if this one is not a point, if this one is a U, so if this is not a point, and then let's say this one is Rn cross U, cross a ball, map to U, and this is just the same thing. You don't do anything on the ball direction. This is the n form, okay? Other question is, can you patch them together? Or the bundle is non-trivial instead. That was the tau isomorphism. That's how you can, if you're on a local chart, this is just this one. This is called a bound function. So this is you should think about the following. You have a manifold M, and then you have a vector bundle. Okay, so each point in M, this is a vector space, which is of Rn. Okay, and the idea was what is the Tom form? So this is a 0 sections. So this is a 0 sections. So each fiber has a 0 here, and the form is just a bump on each. So this is you have this function on the 0 sections times the fiber type directions. So locally it look like that. So usually people just draw as a bump on the 0 section. Okay, the thing is this was globally defined on any bundle. So that was tau isomorphism, and that is, you can see, we basically only use two arguments. Okay, one is the differentiation is a definition of the RAM complex, and then we have integration, which is the inverse of differentiation up to boundary value. Okay, so that was the first argument. Okay, that is giving homotopy and all this. The second argument is you can grouping, and then the reason you can grouping is because of partition of unity. The argument is really rely on partition of unity, and then you can put things together. Okay, once you have that two, and you can put those two together, and that's how you get tau isomorphism. And the next one is so-called Poincare duality. It's the same argument here. Or Conan formula, if you like to. That also worked out for that. Okay, so here's the next. I don't remember which one, maybe 5, 4, 5, whatever property. Poincare duality. It says that the argument that we had earlier about if this one is a manifold of dimension n, then you look at a k form on M, and then an n minus k form on N, and then you wedge together, it becomes an n form on M, and then you can integrate to get R, and it's a perfect pairing. Of course, again, because M may not be compact, so you better be a compacted support form here, and one of them is compacted support form. So this is what we said in the case of Rn, and this is also true in general. Poincare duality, this is a perfect pairing. Proof, the same proof. Proof. First step, it's okay if M is Rn or the ball, it's the same as the because on the That was what we showed earlier. For when ball is true, okay. And then the second step, what is it? One here. The second step is now you write M as two such ball. So it's two. Okay. Okay. So, so that has this called 5 lemma. Yeah. The 5 lemma says the following. If you have a, well, maybe I just write down that and then tell you how to apply 5 lemma in this particular case. Okay. It's a diagram tracing argument. Okay, so what we had earlier was because M equal to U intercept V, so you get H, maybe put it here, HQ of M, okay, you map to, you have this long excess sequence, right? But I say this will be in direct sum, okay? Right? So you get this long excess sequence, and then let's just write down that one. So that would be Q minus 1 of U intercept V, and then Q minus 1 of U direct sum, Q minus 1 of V. Okay. Yeah. And if you do a compacting support, because UV, they are not compacting support. Okay? If you are doing compacting support, remember the thing of reversing direction. And that is the same type of argument that if you're doing compacting support form, you also have this excess sequence, but except now if you're doing compacting support form, let's say P, okay, and then the direction go reverse. So compacting support here, okay. It's the same. You can see what happened. Okay. That's not. But here it tells us that HQ of M is isomorphic to Hn minus Q of M with compacted support. Right? Well, this is what we want. This perfect pairing is the pairing gives you this isomorphism. So you see that the cohomology of M, the compacted support one, the sequence go reverse, but if you take dual, then the thing go backward. Okay? So therefore, now we also apply the dual here, then the arrow go the other way, because the dual sequence, the arrow go the other way. And now it's good, both are going the same way. Okay? And then we know that these two are isomorphic. Because it's isomorphic for U, well, all you need is P plus Q equal to N. So we choose P to be N minus Q. Then this isomorphic, this is because we know it's true for U, and we know it's true for V, and we choose it's true for U index of V, and then this one. Okay? And so on. Okay, so you always have this map because the question was whether it's perfect pairing or not. But even though it's not perfect pairing, you already have the map. Okay, you have a pairing. We don't want this perfect pairing. So you always have this map. The question is whether this map is an isomorphism. Okay. So the question is whether this is isomorphism or not. Okay, we know it's isomorphic. The map is always there. We know it's true when you apply to U, V, or the intersections. And 5 lemma says that if you are in this isomorphism, you have 2 long excess sequence, and then you try to look at one of these terms, and all this diagram commutative. And then you want to know that this one in the middle is isomorphism or not. If all the other 2 on both sides is isomorphic, this is also isomorphism, which is a diagram tracing argument. Okay, so 1, 2, 3, 4 isomorphism. Then 5 lemma said that the middle guy is also isomorphism. Okay, that's a proof. Anyway, once you have 2, and then so that's a 2, and then you do the same thing for more than 2. It's the same argument. Okay, keep on adding more to it. All right, some other property. A couple other property were related to not the argument that we will use. We will use more geometry argument. We will not prove it here. Maybe some other later. Is the following. If M is a compact and oriented, all this argument require the manifold to be oriented in the okay. So this one. This app is isomorphism that require M to be oriented. Okay, that many definition you can say because oriented is a very weak assumption, it's very flexible, and what we really need is the following. Well, this is certainly true for like Rn. Now the question is, can we do integration? Remember, when you do integrations, if you try to integrate du dv or dv du, does it, and that's different. It's a psi here, whatever functions. And have you have a consistent choice of this is the orientation data. So the statement is the following. One way of saying it, which is stronger than what we need, is so orientations, okay, maybe I just write here. Is so you look at a top degree form. Okay, not just any manifold of this. Now, question is, can you find a top degree form? Okay, so what is a top degree form? This is really a section of the wedge end of exterior algebra of this. This is rank 1, okay? This is a rank 1 bundle. Okay. So that is M here, and then you have this rank 1 vector bundle. So this means this is a fiber is isomorphic to R, okay? Top degree form. Now the question is, does this has a non-vanishing section? Okay. Does this have a top degree form which is non-vanishing? That means that V at any point x, mu at any point x is not 0. Okay. So this is called non-vanishing conditions. You can see that this condition is completely topological. You just say that you have a rank 1 bundle, and that condition, if this one is non-vanishing, this is the same as saying that this bundle is topologically trivial, because you can just, I did call this as 1 here, and that's give you, so that condition is exactly the same as saying that this top exterior power of cotangent bundle is, as a vector bundle, is topologically is a trivial bundle. And so you can, if a trivial bundle is a section 1, or if you have any bundle of non-vanishing section, this is called that 1. That is a trivialization globally. So that condition is what we, one way of saying it, this is what we call orientability. If you choose that section, it's orientations. Orientability. And orientation is the, so once you can choose mu, and you can choose another orientation, it's called minus mu. Okay? So this is like the UDV or DVDU. That, can you make that choice globally? Okay. And first of all, once you have this, certainly this top form is 0 because there's no n plus 1 form. So this is automatic. So this clearly will be an element in Hn. Okay? And if M is compact, this one is non-zero, non-vanishing class. And that gives you an isomorphism here. Okay. Let's say M is compact. And that gives you the integration, basically. So that is needed whenever you do the integration on M. You always need it. Okay? If you are in a Thom isomorphism, the fiber is Rn, of course you can integrate. But you can consistently integrate, you need the bundle to be oriented. So, something like that. So I forgot that important, very important notion. Yeah. Okay. So if this is oriented, then if you look at the alternating sum of the dimension, because it's a finite dimension, as I mentioned earlier, of this de Rham cohomology for all k, okay, and that has a description in terms of the, if you choose any metric, any Riemannian metric, G, and then you can get this curvature, Riemannian curvature, And then there is a characteristic class called the Pfaffian of the curvature form, and that will become a top form, and then you integrate it on M. So there's a so first of all, this one is the left-hand side is completely topological. Okay, the right-hand side is Riemannian, depending on choice of the metric, and then depending on the curvature. But this integrate is independent of that choice. Okay. Sometimes these are called error characteristic, as we mentioned before. Okay. And in the case of a Riemann surface, this is a Gauss-Bonnet formula. And this is, in high dimension, this is the Gauss-Bonnet Chern formula. Here is another geometry questions. Okay, so M, again, compact. Okay. And the statement is, so choose any metric with a positive Ricci curvature for the metric. Then the first cohomology is 0. Okay. So these are called. This use Hodge theory. We'll discuss that later. And the Butler formula. And that is a. Yeah. Okay. In a way, we can't see this in the first class, the first day of class. Is this has a generalization to Kähler manifold with holomorphic line bundle positivity. And we use that, these are called the Kodaira vanishing theorem. Okay? When we prove the Kodaira embedding theorem, we use these ones. Yeah. And then we also use this fact that so in a I will explain that the whole cohomology in a second, that in a Kähler case, you have instead of the round cohomology, you have a holomorphic version of that. And then the analog statement will be called the Hussable-Riemann-Roch formula. We also need that to create a lot of holomorphic sections to do this embedding. So this is really the holomorphic version of that is what we said, what we do it in the first day of class. Yeah. Okay, so what we said earlier was this one. If in any manifold, you get this complex. Okay, and it satisfies d squared equal to 0. But remember, d is a differentiation. So d should be d times fg equal to dfg plus fdg something, right? So they satisfy the property that d of a form phi wedge psi is a d phi wedge psi plus phi wedge d psi. Well, the only problem is that this is not a function. This is a form. When you do anti-commuting, you will each time you pass through a form part, then you introduce a minus psi. So this is the number of times that d has to pass through phi. So this is the degree of the phi. Okay. But it's not that important. Just to keep track on the psi. Okay. So this is saying that this d is like a differentiation. So you get a d here. Okay. And this property also tells us that the product from omega k, omega L to omega k times k plus L, okay, is compatible with the D. So that means that this one, so this property tells us that this one can descend to cohomology. In fact, we used that already to tensor wedge product to the top degree form and then integrate, right? And then the integration, as I forgot to mention earlier, was that you need a orientation to do the integration. Okay, so whenever you see integration, you have to assume orientability. Okay, but this property telling you that you have this one, this is a graded commutative algebra. It's just because you might have a minus sign somewhere. Okay. It's a commutative up to its side. Okay, so you get a commutative algebra. I'm going to use this fact for interesting applications to the Hopf algebra structure for the homology of a Lie group. But before that, let me give you some remark here. First of all, the cohomology information. So this is the algebra. It's a algebra, commutative algebra. As I mentioned, it is very easy to compute. But it does not contain that much information, topological information. Okay, it contains still a good amount, but there's still lots more information. What contains lots more information is a homotopy group of M. This information is contain lots of information. But they're very hard to compute. In what sense they contain lots of information? In the sense that if you have first of all, this does not require the M to be a manifold, right? The CW complex or something. If you have a map which induces isomorphism for the homotopy for all K, okay, then M and N are basically the same. Okay, it's a weak homotopy equivalence. Okay, so if M, let's say if we start with N and N are some very reasonable, like a countable CW complex or something. So any very reasonable topological space, that will already imply that M and N are weak homotopy equivalents. So meaning that the group, well, you really need the isomorphism to really come from a map. Okay, then that will be basically control all the topological information that you might want. But it's extremely difficult to compute. Okay. Well, so first of all, just so recall, if you have learned it, if the fundamental group may be more complicated, but if you look at all the homotopy group of not less pi 1, all the others, they are always abelian group. Meaning that it looks like finitely representable abelian. Let's say M is a finite CW complex, for example. So, so that means that this is like Z to some power, maybe plus Z4 or Z7 or something like that. It's a finite presentable abelian group. Okay, so something like that. Okay. So, so pi 1 could be quite interesting though. Pi 1 is not abelian in general. Okay, but is abelianization. That means you take away all the commutator. Okay, that is due to the homology. So that is in fact the first homology group of M with integer coefficient. Okay. So while we are talking about here, let me just give a remark earlier that we mentioned before, that if M is compact with positive rigid curvature, so you choose a Riemannian metric with positive rigid curvature, then H1 of M with R coefficient is 0. Okay? So it does not imply that h lower 1 is 0, because this one could be like z to some power, whatever, 6. It could have torsions. Let's put something like that, say. Okay? So this is 0 is only saying that this part is 0. Okay? You still can have torsions. Okay? But in fact, pi 1 could be even more complicated, because pi 1 could have a very highly non-abelian part. Okay? So this is only capture the abelian information. And so this argument was using Hodge theory and Boolean argument. But if you just do a Riemannian argument, that is even much stronger than that argument. So in fact, of pi 1 is finite. Okay, it's a finite group. Okay. Have you seen this proof? So this is a direct Riemannian proof. It argued the following, that it's a Hot-Morse theory argument that because the manifold is compact, okay, and then if you start with a point, okay, if you draw the shortest geodesic, clarify geodesic, the point is if this is a geodesic and positive Vichy curve, let's say Vichy curvature is bigger than epsilon or something, okay? Then when you're up to a distance, up to something like 1 over epsilon, something roughly, then that has to be a conjugate point. Okay? So conjugate point meaning that, like that. So let me draw another picture. So if it's a positive Vichy curvature, let's say this, just one there, anyway. So it's positive Vichy curvature, you start with any point here, and then you find a geodesic. You start to run the geodesic. And then with positive Vichy curvature, the geodesic will start to hit a conjugate point in a distance depending on 1 over epsilon or something, or epsilon squared or something. So if you go to a finite distance, then that would be a conjugate point. Then once you pass through the conjugate point, then that can never be shortest geodesic anymore, because conjugate point meaning that you can vary the geodesic by fixing the 2 points at least up to first order. Okay, so all these are geodesic of the same length up to first order, bounding these 2 points, and then because once you move this one, then this has a corner here. If there's a corner here, you can smooth the corner to shorten the geodesic. Okay, so that means that once you pass through the conjugate point, then that cannot be minimum. And that, in particular, that means that the diameter of the manifold has to be bounded by 1 over epsilon or something, okay, by the Vichy curvature, lower bound. Okay, and so therefore, if you have this one, the Vichy curvature bigger than epsilon, the diameter has to be bounded in terms of epsilon. And then you take the universal cover of it, then the diameter has still continue to be bounded by the same amount, okay? So in particular, this has to be compact. And the covering group is pi 1, and so it has to be finite. Is it compact by compact? I mean, you have to be finite. It's not infinite, then it has to be non-compact, okay? So because the Vichy curvature has a lower bound, make sure that the diameter is bounded by 1 millionth, and the universal cover is still bounded by 1 millionth, and that has to be finite. So the fundamental group has to be finite, which is much stronger than because it's control even the non-abelian part. Okay, so much stronger than this argument. But the advantage, so there are two completely different arguments. In general, this kind of Riemannian geometry usually have two arguments. One is, this is like a minimum surface type argument. In this case, it's one-dimensional geodesic argument. And the other one is like a Dirac operator argument. Okay? So they have different advantage of depending on the problem. Okay? So for example, this weaker argument that we use here become very powerful in the Kähler case. So there are different generalizations. Okay, let's come back to this. So what I was talking about is the following, that this commutative ring, which is easy to compute, okay, is not as powerful. However, it turned out that if the fundamental group is fine, which is very small, let's say 0, okay? Let's say 0. Suppose this is the case. Fundamental group is the issue. Let's say there's no fundamental group, okay? There's even a stronger statement that while we are here is that if M is Kähler manifold with positive Vichy curvature, okay? So this is a theorem by Frankel. So in the remaining case, it's a positive Vichy curvature, then we just argue that the fundamental group is finite, right? But if the manifold is also Kähler, in fact, the fundamental group has to be 0. More than finite. Okay. So it's a theorem by Frankel. Yeah. So much more powerful, much more constrained than just 0. It's not even that such finite. Okay. So anyway, so let's just come back to this. If the manifold is simply connected, no fundamental group, then this differential form, this complex, contain a lot of information. Then that determines all the homotopy informations except torsions. Okay, torsion could be very difficult to compute. So it's determined that more precisely what it says, it controls the rational homotopic type. Of M. Okay. And or the real homotopy type, meaning that if you real rational homotopy type is you get a map which induce isomorphism on all the homotopy group up to torsions. Okay, that's what it means by rational homotopy type. Okay, so the torsion information cannot be controlled by differential form type argument. Okay, so this is a theorem by Sullivan, maybe Griffith, and I think it's a Sullivan theory. Okay, to be more precise, you need piecewise linear form. Okay. Otherwise, you only construct the real homotopic type. Yeah. So this information is much stronger than the cohomology. Of course, in the cohomology, D will become 0, but the wedge survive, right? But this information is much stronger than this information. This information captures the homotopy. Okay. But then here's a remark, is if the manifold is also Kähler, then that is enough. So if M is also Kähler, then this commutative ring in fact controls the rational homotopic type. Okay, so this I call the formality theorem, and this is proved by maybe Morgan, Griffith, Sullivan. Maybe there's another person I forgot. Yeah, so it uses a lot of homotopy theory. I mean, you build the space with this, how to control that you really build the space by this so-called Pontryagin tower and all this thing. Yeah, so it's a lot of topology morphing. But so you may wonder, can you rescue this thing? Can you do something here? I mean, it seems that this process, you lose a lot of information, okay? And the point is you have to capture this by so-called homotopic perturbation lemma. So that's homotopy perturbation lemma. I mean, homotopy perturbation lemma. Meaning that this one, so this satisfies, what is this satisfy? The property, this satisfy, this is commutative, so this A, B equal to BA up to psi. Or maybe phi psi, maybe I just write phi and psi. Phi psi equal to psi phi. And it satisfies D, phi, psi plus phi, maybe minus of that. D psi equal to 0. And it also satisfies D of D phi equal to 0. Right? This is a commutative ring. D squared is 0, and this is Lipschitz rule. Okay? And you can write it as the following. And then if you write this as M1, write this as M2. So M1 go from MK will go from omega ML maybe K1 omega K2 omega KL to omega sum of the KL sum of the KI plus 1 plus maybe plus L or something. I don't remember, but plus something. Yeah, it's not L. We can check it for this too. And this free property is exactly equivalent to saying that summation. So in this case, we only have M1 and M2. Okay? No, all the other M3 are 0 in this case. All the other are 0. Okay? So these are called differential graded algebra. So this is differential graded algebra. Differential graded algebra. differential graded algebra. And this graded algebra property is the same as the summations. It's the same as saying that M1 plus M2 square equal to 0. Okay? So this is free term. This is M1 square equals 0. This is M1, M2, M1 is 0. And M2 squared is 0. So this is the free terms. Okay? So they come from 3 different terms that are exactly these 3 terms. Okay? And if you look at the cohomology, then of course you make M1 to be 0. But then you can inherit those informations that, so in fact, on the cohomology, so D would be 0. You get a, so the M1 is 0. Wedge survive M2. Homotopy perturbation lemma is you can, the rest of the information you can keep on surviving by adding higher term. Okay, so that exists M bigger than or equal to 3. Okay, satisfy summation of Li to be square to be 0. Okay, this is 2 terms, it's a more term, and these are called A infinity algebra. So yeah. So if you only have 2 terms, that's called differential graded algebra. Okay, But the thing is that you do not really have to be this. You can continue to be rescued up to homotopy, basically. You want to be differential greater algebra up to homotopy, and that's an infinity algebra. Okay? And so that exists of this, so this is a theorem that shows that homotopy lemma said that this one is isomorphic, is equivalent as an infinity algebra to the original. So this is an infinite algebra of two terms. Okay, all the M3 is 0. Okay, and as long as it's A infinity equivalent, that will already. So either this one or that one, that will control that theorem will work. Rational homotopy type. Okay, it means that the cohomology itself does not control the rational homotopy type if pi 1 is 0. But there are further things called the infinity structure that we inherit to rescue it to determine that. Okay? And in the case of Kähler case, they are vanish. So these are sometimes called messy product or something. Yeah. Okay. So at the moment, let me just stop this discussion here because there are lots more discussion. So that's why the A infinity structure in the cohomology is needed, because you want to really capture not just the cohomology, but you want to control the whole topology up to torsion. Okay, so that is the point. So that used a lot in floor theory and almost any of the category theory. This infinity structure. Okay, so let's come back to look at the Q application. Now we can forget the infinity at the moment. Let me just use the following. Okay, so use the fact that if you have a map M to N, then the cohomology of N mapped to the cohomology of M. Okay, this is a ring map. And if you like, you can say A infinity map. Anyway, it's a ring map. It's a ring homomorphism. This is by direct checking, right? This is using this Lipschitz rule. Okay. Well, let's see what can we use this for. Okay. So use this to prove the following statement. If G is a compact Lie group, then G cannot be even dimensional sphere. Okay, this is the argument. Okay, even dimensional sphere cannot, the cohomology cannot be a compact Lie group. Okay, S1 is, S3 is, but not even dimensional sphere. Okay, so here's the argument. Okay, so we have to use the being Lie group, right? So M is a group structure with a multiplication, and then you also have an identity. Okay? So M of E, G is G, right? There's a multiplication with the identity is that. We have these two properties. Okay, so that will induce a map from the cohomology of G to the cohomology of G tensor G. So this is a coalgebra structure, right? Usually algebra is just a wedge product. This is a coalgebra structure. I mean, so eventually the point is when this is a Lie group, then the cohomology has a Hopf algebra structure. You have an algebra structure and coalgebra structure which are related. Okay. Okay, so the point is that the M star of any element here, X, will have something here. Okay, so it's in the tensor product. Okay, so if this is a degree k, then this is degree has to be p plus q equal to k, right? That when you pull back, the degree of the form does not change. So degree k is still degrees p and q together is to be k. Okay. So the claim is it has to have a term which is 1 tensor k, 1 tensor x, and then you have a term which is x tensor 1. And then, so this term has, these two terms will be there, which is y. And then all the other possibility, so this is something called G1, I tensor G2, J, where the I plus J equal to K. And both I and J has degree bigger than at least 1. Okay? So this one is degree 0, right? But the thing is that the degree 0 term here must survive, and they are exactly 1 tensor x and x tensor 1. Okay, then there's something else. Okay, okay, just this. Yeah, and the reason that these two terms is there is because you can look at G. You send to EG, and then you multiply, you get back G. Okay, you can map back from G to G cross G, and you send it to EG. Okay, and then you send it back to G. And then this composition is identity, because when you multiply by E, it's identity. So you look at that, and that will tell you that if you compose it back, this is 1 tensor x. If you look at the other one, it's a GE, it's also identity, then you get the other one is that. Okay? So you use this one, compose it back to here, telling you that this term is 1 plus x. And the other one is x plus 1. Okay? So just using this back. So you're using multiplication and identity. That's the two structures where you use for the group structure. Okay. Then this already implies that X cannot be even dimensional sphere. Okay. So let's say we want to prove that G cannot be S2. Let's say. Okay. Let's say try to do that. Okay. Okay. So let's say otherwise. Okay. Cohomology of G is cohomology of S2, which has two elements. One is 1, one is X. This is in H0. This is in H2. Okay, one tensor x is x, right? And x squared is 0 because top degree already. It's S2. Okay, so you get x0 and h2. All right. So if you look at this, is 1 here. This is a group, right? And then you have 1 here, and then that has to be 1 tensor 1. There's no choice. And then if you look at x, that has to be 1 tensor x plus mixed term plus x tensor 1. There's no mixed term here because this is even dimensional sphere. There's no degree 1 thing here. So there's only 1 plus x and x plus 1, nothing else that you can survive here. That's why we're using even dimensional sphere. So that's it. So 1 plus x plus 1. Those are elements. X also primitive. Yeah. And but then you know that x squared is 0. Well, because x is degree 2 already. X squared degree 4, there's nothing there. Okay, this is 0. So in particular, m of x squared has to be 0. But I just said that this is a ring homomorphism. So m of x squared will be m of x wedge product with m of x. Okay. It's a ring homomorphism. That's why we're using this ring structure here. And so this is 1 tensor x plus x tensor 1 wedged with 1 tensor x plus x tensor 1. Okay. x squared is 0. So you only have one tensor x, which x tensor 1, that's x tensor x. You have two of such terms. That's a non-zero element. X tensor x is in H2 tensor, right? H2. So this is non-zero element in the contradictions. Right? And this type of argument, you can, let me try to see how much you can play with this type of argument. Okay. So this extension of this type of argument. By induction, give the following. Okay, theorem by Hoff. Is that for any compact Lie group, first, the cohomology ring, in fact, you can do this rationally. You only make sure that 2 is not going to be 0 in this argument. Okay, so for example, you can do just characteristic is not 2 or something. So anyway, do it rationally. Okay, as a ring. Okay, it's like odd sphere. Product of odd sphere may not be just one odd sphere. It's always as a ring as a product of some odd dimensional sphere. Okay, it's always a product of odd sphere. In fact, more precisely, this ring is generated by this element. It's a wedge product of this space of a so-called primitive element of G. Okay. So, so what is a primitive element? So an element here is called primitive if this is exactly 1 tensor x, that's x tensor 1. So, so this I mean, just try to understand this argument better. So that was the argument. So in general, any Lie group, from the perspective of cohomology, is like the product of odd-dimensional sphere. Okay, not necessarily 1. In fact, if G is a sphere, that exactly will corresponding to G has to be U1, which is SO2, SO2, or SU2, which is the same as SP1 or spin free, something. Okay. So that only. So this is the unit circle inside C. This is the unit circle inside H. The group structure comes from the algebra structure. Yeah. Okay. So if it is one odd-dimensional sphere, then it has to be S1 or S3. Okay. And the reason they all come from this associative algebra structure. Okay. And but in general, any Lie group is a product of odd sphere from the homology perspective, cohomology perspective. So I'm now going to explain the bow cohomology. But before doing that, let's just recall what we just had. For any manifold, and then you can associate this complex. But in fact, if alpha is a closed one form, if alpha is a closed one form, then you can do a similar thing by adding d alpha. It's still true because d plus, meaning that, d plus alpha. Okay, so alpha is a one form, so you wedge with the one form, you send a k form to k plus one form. Okay, so because this one square, okay, so that is d plus alpha on what? On d alpha plus alpha wedge phi. Okay, and then you do it twice. So this term is d square phi plus d of alpha phi. This is alpha d phi plus alpha phi. Okay, and d squared is 0. Alpha is a one form, so wedge product is skew symmetric. So alpha is 0. Okay, because it's skew symmetric. And how about this two term? Okay, so this two term is so d of alpha phi is d alpha phi plus alpha d phi. Okay, but we already chosen a form which is that d alpha is 0. So this is assumption. D alpha is 0. Okay, so that term is 0. And this term is the same as this term. It's the wrong side. Okay, so just put a minus here. so one is plus, one is minus. It's just a side up to a side. Okay. And then it's 0. So these two terms cancel. So another way of facing this statement is saying that you have a E which is M cross R, M cross let's say C. Okay, so you have a complex line bundle. Okay, and you choose there's a D, which is the usual D plus D alpha, plus alpha. Okay, so for any one form on M, this is a connection on this bundle, and then the curvature is just d alpha. Of this connection. Okay? So that calculation says that so it just says that given a flat bundle, in this case, this is just the trivial bundle. So the notion I write is that just the fiber is constantly C. Okay. with flat connections, meaning that the connection is called flat bundle, meaning the connection is flat, meaning that the curvature is 0, which is what the d alpha is 0 condition. Then you can define this M with coefficient in this bundle. Well, this is just a usual form because the bundle is trivial. This is any form, okay? But then you can define the connections as d plus alpha omega k plus 1 and d and so on. And so the curvature is exactly this composition of this twice, and that the assumption is 0. Okay? So therefore, you can define the same. Once the d squared is 0, you can define the double closure exactly as before, but with a differential form with value in the E, where we're remembering you're using a flat connection. The flat conditions make sure d squared is 0. D squared is the curvature. Okay? So if I'm writing this is really complex coefficient. I mean, you can do a real coefficient too, but yeah. So the statement, so this is in general true, okay? So in general true meaning that you don't need this one. You don't need that one. Given any flat bundle, E, okay? Meaning that you choose a connection whose curvature is 0. And then the connection is really a way to differentiate sections, or you can write form too. Okay, there's a connection. It's really how you differentiate the sections. So you go from k form to k plus 1 form. Okay, and the flat condition is make sure it's exactly saying that this is a complex. Okay, and therefore you can once it's d squared is 0, you can use a kernel over image. Okay, so it's exactly the same as before. A couple of remarks here. So a flat bundle rank, let's say rank, you don't have to be rank 1, but any rank, right? A rank R flat bundle over M. Okay. Okay, well, so definition, the one that we use here, okay, is you have a connection such that whose curvature is 0. Okay. Another way of describing it is in terms of transition functions, and the bundle can be trivialized over some chart. U. Okay, and so you get, so this is just a bundle, the information, right? Any bundle is described by transition functions satisfy the Gij, Gjk equal to Gik. Okay, co-cycle condition. So this is just a general statement about a bundle. And flat condition is the same as saying that you can choose such a thing so that these are constant or locally constant. Okay, so the transition function is constant. Okay, in fact, that is a equivalence statement. Basically, yeah. Okay, and then another statement is this is a Riemann-Hilbert correspondence. Is that corresponding to fundamental group of M to GL of C. It's a group homomorphism. This is because up to conjugations. So the equivalent is D up to gauge transformations is equivalent to rho up to conjugations. Okay. Because you have a lot of flat connection, but up to gauge transformations is the same as for up to conjugation. Conjugate on that. And the reason is the following. Hilbert correspondence. This way. So you have a value for M, and then you have some bundle here. So over each point you have a vector space. So over each point you have a vector space EP. Okay, and if another point you have another vector space EQ. Okay, and what is the connections? As I mentioned earlier, a connection is a trivialization. So a connection is you choose any path here, okay, and then you keep on, then you identify this. We call it phi gamma is isomorphism. Okay, it's a trivialization of the bundle along any path in a consistent way. That means if you have composed a path, then the trivialization has to become the same as the one you have composed. That's the same. So one is, if you differentiate that notion, is a connection. If you integrate the connection, that's called a parallel transport. Okay, so these are called parallel. So the connections, the operator is a differentiation, or if you integrate back, then it's called a parallel transport, and this is the parallel transport. So same notion. So this is just by integration, basically. Solving ODE. So a connection is a trivialization on any path. And what is the curvature? The curvature is if you look at a small path, so you go from x direction, y direction, x inverse direction, y inverse direction. So you look at this small path here, and then look at the above trivialization. You start with this point P here. Okay. And then you look at a vector here. Under this trivialization, this will move to here, and then here, and then here, and then come back to here. It may be a different vector. Okay? That is, so call this the two directions as D1, D2. Okay? Okay? So along these two, and then you look at the smaller and smaller one, epsilon go to 0, and the curvature at these two directions, fix these two directions, will be a endomorphism of EP. Okay? So the curvature is a two-form with endomorphism value. Okay? Which means that you just draw a small square here, just getting smaller and smaller, eventually take a limit. Draw a small square here in these two the two directions, span the square. And then you do this parallel transport, and then see that how much it depending on the path. Okay, you go around, coming back, and that may go to a different element. That is infinitesimal dependency. Because the thing is because the bundle is not flat here. Okay, and that's why you change to a different element. And that's what they call the curvature. Okay, so therefore, if the curvature is 0, then if you move from one path to another path continuously, the trivialization, this identification is the same, because you just write this as a lot of small square. If the curvature is 0, in all the square, there are no corrections. So therefore, the whole thing has no correction by integrating it back. Okay? So the curvature is 0. Is the same as saying that if you choose any two paths continuously, so you have to be a family of paths, so that you have to be able to partition it to the small square, basically. Okay? If you choose two paths continuously, then this parallel transport along the first path, this will be mapped from EP to EQ, these identifications, and the one on the second path are the same. because it's the same on any small path. Okay, so it's the same form. Okay, so it's the same. Okay. The point is that these two paths have to continue to the other. For example, let's say P equal to Q. Okay. So you will be looking at, that means that if you start from any path, if the path is contractible, then parallel transport is identity. So therefore, the only thing is if the path is not contractible, then it's only dependent on what will be class of the graph. Okay. So therefore, this parallel transport, if for flat bundle, will give you a map from fundamental group of M at the point P mapped to the transformation for EP. And then you can compose it, and there's a connection. So this is a group homomorphism. Okay. And then if you write this as the GLR C, then choose any other path, any other trivialization or any part of port that's equal up to conjugation. So, okay, so that was a proof. Okay. And if you have no connections, then remember that the dimensions of the HKM is given by the integral of the Pfaffian of the Riemannian curvature on the manifold. Okay. M is oriented. Okay. There's a Gauss-Bonnet-Chern formula. Okay. If you have a flat connection here, okay. For example, this can be C2, trivial. Okay. Then each C will give you one of such. C2 will give you two of such. Okay. So in fact, the flat condition will not change the effect, and that just gives you the rank of E. So you just multiply this by the rank of E. And that way of writing it, this is the Chern character of E. But in the case where the bundle is flat, the Chern character is the trace of the exponential of the curvature. So if the curvature is 0, this is just a trace, which is the same as the rank of E. Okay, so the whole thing, this what we call the Chern character determine the curvature, because the curvature is completely zero. All the contribution is a rank. Okay. And why would I want to write in this trivial way to be so complicated? Because the next one is in the Debol cohomology. The corresponding formula is the Riemann-Roch formula, the Chern character times the Todd classes. Okay, because in that case, it's not flat anymore. Okay. So before we go to the Debol cohomology, we have no time. There's one more thing that we need is if you have a flat bundle E, and then you have a flat subbundle, and you have a flat quotient bundle. So all of these are flat bundle. So this means that you have a flat connection, flat connections, flat connections. Okay. Then, in fact, for example, this map, let's just call this one F and call this G. Okay. So S is a map from S to E. So F is really a section of S star tensor E. Right? And then the condition is this one is flat, meaning that this is the same as saying that if you have a flat section on E, F of that is a flat section on E. Okay, it's the same condition. This condition, so this is a exact sequence of flat bundle requiring that F as an element here is flat with respect to the connection on S and the connection on E. Okay, and this condition is the same as saying that for any local flat sections on that, so ds is 0. Okay. Then after you compose with that, so that will be a section on E, local section, and this would imply then on the bundle E, this one is flat. Okay, you have to make sure that because both S and E are flat bundles, so you have to make sure that you send flat section to flat section locally. Okay, and that's the same as saying that this itself is flat. But this is just because it's obvious, right? D of Fs is the same as dFs and then Fds. So that's why it's the same. Okay, but the point is once you have this, that will give you cohomology of S mapped to cohomology of E as usual, and so on. And you get long exact sequence. Same type of homological argument as before. Okay. Okay, so maybe I really should really be careful about the bulk homology next time. But let me say a few words here. Just a remark that will I'll explain in more detail next time. So if you have a manifold M, then you get D on the form satisfy D squared is 0. And that's why you get the bulk homology. And then you have variation and all the theorem. And then you have an extension to the case that if this one is a complex manifold, then in this case, that the tangent bundle tensor with C splits into 1 0 part and 0 1 part. The same for the cohomology on the cotangent bundle. This is eigenspace of eigen. So J square minus 1 has eigenvalue I and minus I here. Okay, and so therefore the differential form of complex coefficients will be direct sum of differential form of the corresponding one. It's called the PQ form on M. And then the operator D from K form to K plus 1 form. So this is an almost complex structure. The complex structure telling you that this split into D and D bar. Okay? For almost complex structure, you have another N and N bar, which is 0 when this is complex structure. Okay? And because of this, D squared is 0 is the same as D squared is 0, D bar plus D bar D is 0, and D bar squared is 0. We are mostly interested in holomorphic functions, so really the D bar is the thing that we really care. And so you get D bar, it goes from PQ to PQ plus 1, and D bar square being 0 gives you the cohomology. It's called PQ cohomology of M. Notice that we're using the D bar here. Okay. So the same type of thing, but now if you have a holomorphic bundle, is saying that the transition function is holomorphic. So transition function is from something like a UI, this is a UJ, so this is something inside Cn, and then map to this matrix, right? So we require this map is a holomorphic map. Okay. That is the same as saying that you can group, before it's like flat, then you can group the D, right? Now you can group the D bar. So you get this on this one. You can send it to 0 Q form to 0 Q plus 1 form. Or you can do the PQ too, maybe just a P. Okay. The thing is that you can only have a D bar, you cannot have D. Only D bar square is 0 in this case. That's why we are, because of all the things we really care about holomorphic function, holomorphic section, and so on. So you can only have D bar square of E is 0, not the D square. Okay? And so therefore you can also have the analog of the flat bundle. This is like an analog of the flat condition. But of course this is much easier because we are not looking at a completely locally constant function. And this is a locally holomorphic function. Of course this is a lot more than constant function. Okay, so there are a lot more holomorphic bundles. So this becomes very powerful that you can talk about D bar of this. One remark that, let's just say here, this is the same as this bar of M wedge P of the cotangent bundle tensor E. Okay? So you don't have to, you can put the P form here too. And one thing is, of course, you have a Hodge theory, decomposition, but one thing before we stop here today is, so first of all, there are a lot more holomorphic bundle than flat bundle. Because you only require not locally constant, just holomorphic function. That's a lot. Example. Another important thing that we have compared to this is if you try to do the same thing, if this is E, holomorphic bundle, all these are holomorphic bundle, this is S, okay? And then Q will be the quotient, E by S. Okay? Now, all you need, previously, we need this to be constant. Now you only need holomorphic. So you only need D bar of F for this bundle thing, maybe S tensor E, to be holomorphic. This is much easier than being constant. One of the things is if this is, so F is a what? F is a, at every point you have a matrix. So if this is constant, locally constant, then the rank has to be constant. Holomorphic functions can vary. It can be 0 here, not 0 there. Constant function is 0 here, is 0 there. Okay? So that does not imply constant rank. Meaning that the quotient is not a bundle. And that's what we usually call a coherent shift. Okay? Coherent shift is locally, you can write as a bundle quotient by, maybe a bundle quotient by another, locally, bundle by another bundle by F being holomorphic. Not, okay? So because if it's flat K, you don't get anything because it's constant rank, it has to be constant rank, has to be bundle. But quotient is what we usually call coherent shift. There's a definition of coherent shift. Meaning that locally is the E quotient S by something which is holomorphic family. Okay? And because of this long excess sequence behavior, you can define all the cohomology, everything for coherent shift. Because of a lot of this functorality property. Because once you know S and E, you control whatever the Q. So the cohomology theory can be completely defined for coherent shift. Okay? Because of functorality, or like this type thing. You continue to have that functorality. If you call the coherent shift S, okay? and then you can define the local homology for any coherent shift. And then they have all the other property that looks like for vector bundle. Okay? But this is a lot more powerful. It's like bundle which can be singular in a holomorphic way. Okay? And this make why all this complex geometry is a lot more powerful than manifold theory.